In the video about visual displays for two variables, we considered how the variable types determine the appropriate visual display to use. In this video, we consider the appropriate methods of analysis for situations where we measure one numerical variable and one categorical variable across a number of subjects. Consider two brands of AA batteries, where brand is the categorical variable. We may be interested in whether or not the two brands have equal or differing mean lifetimes. Battery lifetime, measured in minutes, is the numerical variable. Those in marketing may like to advertise that their brand lasts longer, for example. To test this, we take a sample of batteries from each population and measure their lifetimes. An independent two samples t-test essentially considers how great the difference in sample means is relative to the amount of variation in the data. A large difference in the sample means and little variation would suggest the population means differ. If there is a large amount of overlap and/or the sample means are close to one another, then we are likely unable to say the population means differ. Consider the case of needing to assess whether exposure to a toxin affects concentrations or amounts of a substance in the brain. A group of 18 rats, referred to as the treatment group, are exposed to an environment containing the toxin, and a second group of 18 rats, referred to as the control group, are not exposed to such an environment. For each rat, we would measure two variables. One is toxin exposure, which is categorical, with possible responses yes for treatment group or no for control group. The other is concentration of substance in the brain, measured in nanograms per gram, which is numerical. We have 36 rats. For each, we measure these two variables. The result for a rat exposed to the toxin is not related to the result for one not exposed to the toxin, so we may consider an independent two samples t-test. If the sample of 18 rats not exposed to the toxin produced a mean concentration of 450 nanograms per gram, and the sample of 18 rats exposed to the toxin had a mean concentration of 520 nanograms per gram, does this mean there is a difference in the two population means? We can see the two sample means differ, but does this translate into the two population means differing? It depends upon the amount of variation about each of the means. If the sample mean of 450 was the result of every rat in the control group having a measure of 450, and the mean of 520 the result of every rat in the treatment group having a measure of 520, then it would seem there is strong evidence, based on the samples, that the two population means would differ. However, what if the values in each group were more widely spread, such that, as would more likely be the case, not all concentration amounts are the same within each group? Considering we are simply taking a sample from each population, and hence there is an amount of uncertainty about what the true population mean may be, when there is a lot of overlap between the values in the two sets of data, we may be less sure of whether the population means differ from one another. So the size of the difference in means, known as between-group variation, and the spread of the data within the two groups, known as within-group variation, and how much they overlap, as well as the sample sizes, all impact upon the strength of evidence that the two population means differ or not, as we are only considering samples and inferring about the population. To perform a formal test for a difference in the population means, known as the independent two samples t-test, we first use some notation for brevity. For our situation, mu control and mu treatment could respectively represent the population mean substance concentrations for those in the control group, those not exposed to the toxin, and those in the treatment group, those exposed to the toxin. Then the null hypothesis, denoted by H0, would be that the population mean substance concentration for those in the control group equals the population mean substance concentration for those in the treatment group. We calculate, or the computer calculates, the probability of observing the current difference in sample means if the true population means were equal. That is the p-value, which is a probability and hence a value between 0 and 1, and gives the strength of evidence against the null hypothesis. The smaller the p-value, the greater the strength to reject the null hypothesis. We compare the p-value with what is known as the significance level. A commonly used significance level value is 0.05. If the p-value is smaller than the significance level, we reject the hypothesis that the population means are equal at that significance level and conclude they are statistically significantly different. Else, we cannot reject the null hypothesis. This has hopefully given you insight into the hypothesis testing process for two independent populations. We now consider the situation where we have a natural pairing between measures made across two populations. That is, they are not independent measures. For example, if we were to assess a new medication's ability to reduce pain, we would measure a person's rating of pain prior to the medication and then again after administration. We again have one numerical variable, pain score, which may be a score from 0 to 10, and one categorical variable, timing of measure relative to the medication being administered, either before receiving the medication, referred to as pre-medication, or after, referred to as post-medication. For 8 patients, we may record the data as follows. Do we simply want to compare the mean of the pain scores of the group of 8 before the medication with the mean of the pain scores of the group of 8 after the medication? We really are more interested in the change in pain score for each person from pre-medication to post-medication. So we are more interested in the series of 8 differences in pain scores, pre- and post-medication. We are conducting a paired t-test. The situation reduces to be equivalent to a single population hypothesis test, where the single population is a population of differences in pain scores. The null hypothesis is that the population mean difference in pain score equals 0. The sample mean difference of our 8 patients is 0.625, found by summing the 8 differences and dividing by 8. We want to know the probability of observing a mean difference as or more extreme than 0.625 given the variation in the data we observed, if the true population mean difference was 0. As before, we utilise the p-value to make a decision surrounding the strength of evidence against the null hypothesis.